Here's a fact that modern neuroscience cannot explain. You are watching this video right now. Somewhere inside your skull, 86 billion neurons are firing in patterns we can map, measure, and model. And yet, no widely accepted scientific theory fully explains why it feels like something to be you. Why there's a you are experiencing any of this at all. That gap between physical processes and subjective experience is known as the hard problem of consciousness. And the answer, when we follow the evidence honestly, may not end in the brain alone. It could extend into deeper structures of reality itself. In 1994, a cognitive scientist, David Chalmers, stood up at a conference in Tucson, Arizona, and said something that made the room go quiet. He drew a line between what he called the easy problems of consciousness, explaining how the brain processes information, responds to stimuli, controls behavior, and what he named the hard problem. Not hard as in difficult, hard as in, we still don't have a clear scientific framework that explains it. The hard problem is this: why does physical process give rise to experience at all? Here's the real mystery. Your brain is constantly processing information, signals, patterns, reactions, but why does any of it feel like something? Why isn't your brain like a song being played with the volume turned all the way down, every note, every rhythm perfectly structured, but no sound is ever heard? That's the mystery. The structure is there, the core is active, but where does the feeling come from? And why is it there at all? We can increasingly map and model neural activity. We can trace every electrochemical signal across parts of the brain. We can build models of how your brain handles vision, memory, language. But none of those models explain why you experience the color red as red, why music moves you, why a memory can make you feel like you're actually there. For decades, the dominant assumption in neuroscience has been that consciousness emerges from complex brain activity, and that as our models improve, the explanation will eventually follow. But that assumption is now being questioned, not rejected, but pushed to its limits. Some preliminary studies in quantum biology suggest that the data is something that, while still debated, is difficult to ignore entirely. To understand where this goes, we need to start with one of the most disturbing experiments ever conducted. Something so strange that the late Richard Feynman, one of the most influential physicists of the 20th century, called it the central mystery of all of quantum mechanics. It's called the double-slit experiment. And here's what happens. You fire particles, electrons, photons, at a barrier with two narrow slits. When you don't observe which slit they go through, the particles behave like waves. They create an interference pattern on the screen behind them, as if each particle went through both slits simultaneously. But the moment you add a detector, the moment you observe which path the particle takes, the interference pattern disappears. The particle suddenly behaves like a particle. But when a measurement is made, when the system physically interacts with a detector that can determine which slit the particle passes through, the interference pattern disappears at the quantum level. The particle behaves differently depending on whether that information exists in the system. This isn't a measurement error. This isn't an artifact of equipment. This has been replicated thousands of times in laboratories around the world. Physics has a word for this: wave function collapse. Before observation, a particle exists in a superposition of all possible states simultaneously. The act of measurement collapses that superposition into a single definite outcome. What this means is that, at the most fundamental level we can measure, quantum systems don't take on definite states until they interact with a measuring system, which philosophically is still debated. And the question that quantum mechanics has never fully answered is, what exactly counts as a measurement, and where, if anywhere, consciousness fits into that process? That question led two scientists to one of the most controversial and consequential theories in modern physics. In the 1990s, Nobel laureate mathematician Roger Penrose and anesthesiologist Stuart Hameroff proposed a theory called orchestrated objective reduction, OR. The premise is controversial, but worth examining. Inside every neuron in your brain, there are structures called microtubules, protein scaffolding that most scientists assumed was just structural support. Penrose and Hameroff proposed something different. that microtubules are capable of quantum computation, that your neurons aren't just processing information like a classical computer, they're doing something quantum, something that operates at the boundary between the physical world and the quantum vacuum beneath it. The theory suggests that consciousness arises from quantum processes inside these microtubules, and critically, that those processes are connected to what Penrose calls objective reduction, a proposed process in which quantum states collapse due to fundamental properties of space-time geometry itself. This idea is not part of standard quantum mechanics. Most physicists interpret quantum collapse using other frameworks, and Penrose's proposal remains speculative. In other words, consciousness isn't generated by the brain. If their hypothesis is correct, the brain is a quantum receiver, tuned to a frequency that exists in the deep structure of the universe. When OR was first proposed, most physicists dismissed it. The brain, they argued, is too warm and too wet for quantum coherence to survive long enough to matter. Then the experiments started coming back differently. In 2024, researchers at the University of Vienna detected quantum entanglement in tubulin proteins at physiological temperatures, inside the kind of biological environment that was supposed to make quantum effects impossible. MIT published direct imaging of quantum coherence in living mitochondria the same year. The thermal noise, the most powerful argument against auto, quietly lost ground. What if your brain isn't creating consciousness, but receiving it? If consciousness is rooted in the quantum geometry of space-time itself, not in the biology of any individual brain, then what we call your consciousness may be less like a flame your brain produces and more like a window your brain opens. Physicist Max Planck, historical quantum theory perspective, said something in 1931 that was largely ignored by the scientific community that came after him. I regard consciousness as fundamental. I regard matter as derivative from consciousness. What Planck was pointing toward, and what the latest quantum biology data is beginning to support, is a model of consciousness not as a product of complexity, but as a field, an emerging hypothesis of the universe. Something that doesn't emerge from matter. Something that matter emerges within. If that's true, and while the evidence isn't yet definitive, it's becoming harder to dismiss. The implications extend beyond neuroscience. They begin to shape how we think about the possibility of other minds, which leads to a broader mystery, the Fermi paradox. Remember the Fermi paradox. The question of why the universe, old enough and vast enough to be teeming with intelligence, is so silent. One hypothesis we explored was that advanced civilizations evolve beyond electromagnetic communication entirely. If consciousness is a fundamental field, not local to any physical brain, not bound by the speed of light, not detectable on the electromagnetic spectrum, then the silence of the cosmos isn't evidence that we're alone. It's evidence that we're not yet tuned to the right frequency. We've been scanning the sky with radio telescopes. But what if the most advanced minds in the universe don't broadcast? They resonate. What if the conversation has been happening all along, at a level of reality we're only now beginning to have instruments to touch? If that question resonates with you, if you find yourself at the edge of what science officially says and what the data is quietly suggesting, this channel is built for exactly that space. Subscribe.